Good afternoon all. Today I am myself Nupur Mittal. I am a faculty from Ajay Kumar Garg Engineering College. Today I am going to deliver a lecture on the topic block diagram representation. So these are the basic outlines of today's lecture. First of all, I will let you know what is block diagram, why there is a need to use the block diagram representation system. Then what are the different components we are using in the block diagram for making a block diagram. Then what are the basic connections that are being used in the block diagram representation. Then we'll discuss some transformation theorems of the block diagram. And at last, we'll discuss some numerical problems that are based on the block diagram representation system. So, first let me tell you why there is a need to use a block diagram representation. See, sometimes a given network, given system, is complicated in nature. So, it is very difficult to analyze the complex system as a whole, right? So, sometimes we convert that system into we can analyze that system by using the transfer function approach, right? Then by using the transfer function approach, it is also a difficult task, and time-taking task to analyze the system. So this block diagram representation comes into the picture. So we can calculate the transfer function of each and every element of the physical system, and then by connecting them through the blocks, we can represent each an element through a block by calculating its transfer function, and by collecting all these elements, we can make a block diagram of the particular physical system given to us, and we can analyze it very conveniently. So basically, this block diagram, it is a shorthand graphical representation of any physical system which is defining a relationship among all of its components. Or you can say that block diagram, it is a pictorial representation of the system. It basically defines the cause and effect relationship of the input on the output by using the blocks, through the blocks, right? So the simplest form of the block diagram is the single block, right? Single block with one input and one output, okay? In the previous lecture, I have told you that a system can have a single input with a single output, that is called as a seesaw system, and a system can have a multiple inputs with the multiple outputs, that is called as the MIMO system. So the simplest form of the block diagram would be a single block. Block is basically represented by this rectangular box. I'll tell you about this in the next slides, okay? Then we have a single input applied on this particular system, right? Let this block is represented by GS, right? And we are having input here as XS, and the output will be here as YS. So this is the simplest form of representing an element, any element, through the block diagram representation, where we are having a single block which is representing a transfer function of that particular element. It is represented by GS, right? And this XS is the input here, and YS will be the output here. Now let us come to the different elements of the block diagram, or you can say components. So basically, there are four components that are being involved in the representation of the block diagrams, right? So one is the signal, then we can say block, or you can say a system, then a summing point, or you can say a summing junction, and the last one is the takeoff point, or you can say it as a pickoff point. Now I'll discuss all these components one by one in brief. So first we'll talk about the blocks, okay? What is a block? This block is basically represented by this rectangular box, okay? This block is having a transfer function of a particular element inside it. See, you can see this is the picture. In this figure, this GS is representing a block, and this rectangular box is a block with a GS written inside it. This GS is representing a transfer function of any particular element, okay? And here you can see this block, basically it is representing a mathematical approach of the system of the input, right, on the input by the block to produce a particular output. Here you can see this ys, this signal xs will get multiply this transfer function gs to produce the output ys, right? So second one is the signal, right? So these signals, these can travel along the direction of an arrow only. They cannot travel against the direction of the arrow, right? These signals are basically represented by the arrow, and these arrows are representing the direction of information, or you can say the direction of the signal flow. So basically these arrows, these signals are unidirectional in nature, okay? And you can say that the block diagram is a unilateral property of any particular system. So for this system, you can say the ys output will be the multiplication of the input with the transfer function inside the block gs. So here ys will be equals to xs into gs, okay? So coming to the next, that is summing point, or you can say summing junction. This basically summing point is represented by a circle, okay, with a cross inside it, okay? So it can, here you can have a number of inputs. Any number of inputs can be applied to the summing point, producing a single output, okay? Basically the output is this output, let y is the output. It is the algebraic sum of the inputs applied to this particular summing point. It depends upon the signs. With the help of summation, we can perform the operations of addition, subtraction, or a combination of both addition and as well as the subtraction, right? See, this is the example. Here you can see on this summing point, we are having three inputs A, B, and C. And it will produce, you can see here, the A, B are the inputs with the positive polarity, while C is the input with the negative polarity. So output Y will be the sum of A and B with the minus sign along with C. So Y is the output, which will be equals to A plus B minus C. Okay. This is the another figure. Here you can see we have two inputs applied to this summing point, A with the positive polarity and B with the negative polarity. So output will be the difference of these two input signal, A minus B, right? In the third case, you can see we have two inputs A and B. A and B both are with the same polarity, that is having the positive polarity. So here the output Y will be the addition of the two input signals A and B, that is A plus B. So any number of inputs can be applied to a particular summing point, okay, but depending upon the polarity, output will be produced. So coming to the takeoff point, or you can say it as a pick-off point. So this takeoff point is basically a point from which the same input signal can be passed through more than one branch. That means with the help of this takeoff point, we can apply the same input to one or more blocks or to one or more summing points, right? It basically distributes the input signal, or you can say the output signal, without any alteration in that particular signal to several points, to several outputs, to several inputs, right? It basically permits to proceed unaltered along with several different paths to several destinations. See here, I have shown the two figures. Let me talk about the figure 2 first, then I'll discuss with this about this figure. So here you can see this is a figure for the closed loop system. Okay, you can see here GS is a forward path transfer function this is the block here, RS is the input, this is the summing point, and this is the takeoff point. Here, first of all, note that this closed loop system is a unity feedback system. Unity feedback means here HS is equals to 1. So it is represented by a single line instead of any block. Okay, you can also represent it by a block with written 1 inside it. Okay, so here you can see this takeoff point means a part of the output CS. You can see here a part of output CS is fed back through this feedback signal to the summation point. Okay, then from their summation point, RS is being compared with this CS and a signal will generate here, which get multiplied with this transfer function and will get the output. So basically you can see that the same point, the output which is here at this particular node, it is given to the another block, right? Or if we remove this block, it is given to this summing point. One is given to this output, one signal is given to the output, and from the same point we are giving the feedback signal to the summing point. Here you can see in this figure, this is the takeoff point. This RS being provided to all the 3 blocks with the help of this point. You can say from the same node. Okay, this RS goes here, same signal, that means RS goes here without any alteration, and it goes here, so RS. So here CA will be, this RS gets multiplied with GAS and will get the output as CAS. So CAS will be basically RS into GA of S. Similarly, CBS, the output of second signal, will be RS into GBS. And similarly, CCS will be RS into GCS. So the same point instead of giving the same signal 3 times to 3 different blocks like this, RS, then again I am giving here RS, and again I am giving here RS to GAS, GBS and GCS, right? So instead of giving the same signal to different blocks, we can use the takeoff point, so that same signal can be given to different blocks or different summing points. So let us consider this example. Here we have, let us consider this equation in which x1, x2, x3 are the 3 variables and a1 and a2 are the coefficients, or you can say mathematical operators. Now we have to draw the block diagram depending upon this equation. So you can see we have the variables x1 and x2, and we have the equation written in terms of x3. So you can see x3 could be the output, right? And we can say x1 as one of the input, right? Let me make it here. X1 as one of the input, and we have another input as x2. And they said that we are having a1 and a2 as the coefficient, right? Sorry. A1 and A2, and another is -5, right? So we can produce the output using the summing point, that is x3, right? We know x3 is the output in this equation. So A1 get multiplied with x1, right? This is the signal. A2 get multiplied with the signal, and we can put it a plus sign here. We can put a plus sign here, and then we are having -5, a variable. We can directly apply -5 and give it to this, or you can say we can apply minus sign here and plus sign here. 5 is given here, and this will be x3 depending upon this. See, you can see this 5 can be directly given to here, or you can draw this figure and write this. You can, through this equation, you can draw this block diagram. Okay. Now, what are the basic connections that are being used in the block diagram system? The first one is the series connection, also called as the cascade connection. Basically, in case of series connection, any number of blocks, they can be combined algebraically, okay. They can be connected in series. Any number of blocks which are connected in series can be algebraically combined by the multiplication of the transfer function, right? Let's say we are having two blocks which is having a transfer function g1 and another block is having a transfer function g2, and these are connected in series, okay. See, this is the figure, okay. So you can represent it with a single block and multiplying their transfer function. You will get the same output as here. I'll show you with the derivation here, okay. Now see, this is the figure, okay. Ys here is the output, okay. Xs is the input and Zs is the signal in between, which is coming from the multiplication of Xs into G1s, right. So you can write when any number of blocks which are connected in series, their transfer function get multiplied to give a single transfer function of that particular block. See here, you can see Ys is the output. So we can write Ys as G2s into Zs, right? And Zs can be written as Xs into G1s. Okay. So you can say, we can put the value Zs here, okay. So Ys will be equals to, this is the value of Zs. So Ys will be equals to G2 into G1 into Xs. And when we combine it, you know Xs is the input, right? You can write it in this form. So Ys will be equals to combination, multiplication of these two transfer function into the input. So the transfer function here could be G1 into G2. That means we can represent a series connection of two blocks or n blocks, n number of blocks with a single block, okay. So basically, the single block is the product of a transfer function of those n number of blocks, and the equivalent diagram could be this. I have already told you Ys will be equals to G1 into G2 into Xs, and it could be possible for n number of blocks which are connected in series with each other. Now coming to the parallel connection. So blocks which are connected in parallel, they are having the same input, the same signal. See, you can see here, this is the takeoff point, and through this takeoff point, Xs is given to G1s block and Xs is also given to G2s block, right? So parallel system may have a common input, and the output formed by the parallel system will be the addition of the output of the subsystems. See here in this figure, we have two blocks which are connected in series, parallel, G1s and the G2s, right? So the output of these two blocks will be the summing point. Here you can see Ys will be equals to Y1s and plus Y2s, right? Where Y1s is equals to Xs into G1s, and Y2s will be equals to Xs into G2s, right? So Ys will be equals to, we can write G1s plus G2s into Xs. See, from here you can conclude that output will be the addition of the blocks, right? Two blocks, output will be the addition of the blocks which are connected in parallel. And these blocks are basically, these are the transfer function of the blocks. So here you can see, we can represent Ys is equals to this, and we can represent it with a single block. See, I have all shown that this is Ys, you can see here, Y1s is this, Y2s is this, then Ys comes to be this, and then finally it is coming out to be like this. And when we compare it, we are getting Ys is equals to Gs, then Gs will be the G1s into Gs. And we can represent it with the single blocks with the combination of, with the addition of two blocks transfer function of the two blocks. right? Similarly, we can do it for n number of blocks. If n number of blocks are connected in parallel, we can represent it with a single block which is containing the sum of the transfer function of all those n blocks. Now coming to another example, which is example for the parallel blocks which are connected in parallel. See here, you can get CS. CS will be the RS into G1S, RS into G2S, RS into G3S. The summation will be the CS. You can see here, CS will be, we can take RS as combined, so CS will be, since I have taken here plus minus sign, both the signs, so CS will be with the signs G1 plus plus minus G1S plus minus G2S plus minus G3S into RS. And you can represent it with a single block, that is this. So the equivalent transfer function will be this. Okay. Now coming to the feedback connection. In the previous lecture also I have discussed about the feedback connection which is involved in the closed loop system, right? There are basically two types of feedback. One is the positive feedback, another one is the negative feedback. We always prefer the negative feedback. Okay. So these are the three figures which are representing the block diagram only. Okay. In the first figure, figure A, we are representing the feedback control system. This is representing the simplified model, right? And this is basically representing the equivalent transfer function which we'll get after the reduction. Okay. So this particular system, control system, it is having a controller, it is having a plant. Every element is being represented by a block which is containing the transfer function, right? And these now, after simplifying, we are representing it with a single block. Okay, since these are connected in series, we are connect them with represent them single block. Similarly, these are connected in series, we can represent them with a single block again. And this is finally the simplified model. Now this can be converted into a single block with this transfer function. Now as I have already told you about how to get this transfer function, in the previous lecture I have already discussed how to get this transfer function. Okay, so this block can be simplified into a single block, right, where CS upon RS will be equal to GS upon 1 plus minus GSHS, right? So this plus will be for the negative feedback and minus will be for the positive feedback. It is depending upon the polarity. Now these are the reduction techniques. I have already discussed about when the blocks are connected in series or in cascade, they can be represented. Since here two blocks are represented in series, they can be represented with a single block, and the transfer function will be the multiplication, okay, of the two blocks. Here again I have already show you in the previous slide that when two blocks are connected in parallel, they can be represented with a single block with the summation of the transfer function of the two blocks. Now coming to the third one, which is moving a summing point behind a block. So sometimes there is a need to move the summing point or to move the block behind the forward to the block or forward to the takeoff point. So we need to make changes in the block diagram so as to simplify it, right? So for these, for the simplification purpose, we can transfer our block behind a moving summing point or beyond the summing point. Similarly, we can move the takeoff point behind the block or beyond the block, right? So here we have moving a summing point behind a block. The point which is to be kept in mind is there must be no change in the output. We can move the block, we can move the summing point, we can move the takeoff point beyond another component or element or behind another component or element. But the point to be kept in mind is that there should not be any change in the output. Okay. So this is one of the point when we have to move a summing point behind a block. So whenever we move this summing point behind this block, you can see here we are having let this x be the output here, and when I move this summing point behind this block, that means here, so we should add a block of the same transfer function to this summing point so that there must be no change in the output here. Okay, you can see here we are let me tell you, if I am getting let it is x1 the input, and this let be the y2 be the another input. Coming to this summing point, will have the output here like x1 minus y2, right, which gets multiplied with this g and will get the output as x3. So here you can see x3 will be equal to x1 minus y2 into g. Okay, now this output must not be changed when I move this summing point behind this block. Now let's see here again, this is x1, right? When this x1 is gets multiplied this g and coming to this summing point, let's say I have not introduced this block g here. See, this x1 when it get multiplied with g and coming to this summing point, right, which is having, let's say, y2 as the output, then what will be the here, x3 is already the output and y2 is actually here nothing but negative sign ke saath tha, and this is positive, right? So we'll get here x1 into g, right, and y2 is coming to here. So here you can see x3 will be x1 into g plus y2. So you can see the difference between the two outputs. That means x1 into g is already present here, but y2 here is alone. Sorry, this will be the minus y2. y2 here is alone, while here we are having a block g get multiplied with this y2, right? So because of this change in input, we have to multiply this y2 with a block which is having the same transfer function in this block, that is g. Now when I multiply this y2 with this g, I'll get here y2 into g. Now you can see there is no change in the output. So whenever we move a summing point behind any block, we need to add a block in series with the which is having a same transfer function as that of another block, and this block needs to be connected here in series with the summing point. Now coming to the another point, that is moving a summing point ahead of a block. Now you can see again here g, let's g there is one input x1. When I multiplied this here, I will get x1 into g, let this will be the x2, then we'll get x3. Output will be x1g minus x2. So whenever we'll move a summing point ahead of a block, we have to connect a block with the reciprocal of the block we are having with us, with the reciprocal of the transfer function of a block, right? So here again you can see when I have introduced this, transfer function, reciprocal of this transfer function, then you can see I will get here the input as only x1 from here. Okay, here x1 is coming, x1 is coming here, and let this be the x2. Then what will be there here? We'll get here as x1 minus x2 upon g, right? And when this whole gets multiplied with this g, we'll get x3. This will be x3. So you can see here in both these cases, the output will be same. So there is a need to add a block which is having a transfer function as a reciprocal of the transfer function of the same block. Okay, now similarly moving a pick-off point behind a block. When a takeoff point is to be moved behind a block, here we have to add another block which is having a transfer function as the reciprocal of that particular block. Okay, similarly when we move the takeoff point ahead of a block, so then this block same a block needs to be added in series which is having the same transfer function as that of this particular block. Similarly, when we have to eliminate a feedback loop, we have already discussed about this in the previous lecture only. A feedback loop can be represented by a single block, okay, and which is having a transfer function g upon 1 plus minus or minus plus gs. It is this plus minus or minus plus will depend upon this polarity. If we are having positive sign here, we'll put negative sign here, and if we are having negative sign here, we'll put positive sign here. So this will be the transfer function of any particular feedback loop. Okay, and when we have the feedback loop gain as 1, h is equals to 1, then it can be represented by this. You can put the value of h here 1 in this equation, you will get this. Now swapping the two neighboring summing points, that means the associative law. This associative law holds good for block diagram representation. See here, you can see here, we are having these two summing points. One is having the input minus a and another one is having the input as minus b. Let's say this will be the input x1, then here we are getting x1 minus a, which get x1 minus a, okay. Then this x3 will be equals to x1 minus a minus b, x1 minus a minus b. Now associative law says we have to swap these two neighboring summing points so that output may not get altered and we can easily simplify our circuit, okay, our system. Now here again x1 is the input, x1 minus b will get here x1 minus b, right, and another minus a. When we come here, then x3 will be x1 minus b minus a. See, there is no change in the input. When I have swapped these two summing points, but the point to be kept in mind that we have to swap along with the polarities of the input signal. Don't forget to change the polarities of the two input signal, okay. Now these are the some reduction rules of the first we have of the complicated block diagram. So first you should simplify the series connection, then go for the parallel connection, right, then simplify the feedback loop system, and if there is a difficulty with the takeoff point while simplifying, then try to shift it towards the right. And if we are having any difficulty with the summing point, then try to shift it towards the left. And you can repeat all these steps one by one until you get the simplified form of the block of the system, that is we are getting until you get the single block, okay. So this is one of the example. So here you can see we have to simplify this block diagram, okay. We have to find out the transfer function, that is ys upon rs. So the first approach is to simplify to see whether any blocks are connected in series. So first simplify them. So here you can see these two blocks are connected in series. So I can convert them in a single block with the multiplication of their transfer function, simply like this, okay. And similarly, second point, first point is this, second point we can check that any blocks are connected in parallel. You can see here these two blocks are connected in parallel. We can again simplify these two blocks with the single block with their sign addition G3 plus G4, right. See here I have change it into a single block G3 plus G2, and similarly these series blocks are connected, simplified and converted into a single block G1 into G2. Now third step to simplify the feedback loop. One is loop is here. This could be the loop, but because of this takeoff point we cannot solve it. So we have to resolve this takeoff point, either shift this takeoff point. So first let me solve this one. This is the feedback loop. So it will be converted into a single block like this, right? Forward path transfer function upon 1, since it is a negative sign, so 1 plus forward path transfer function into reverse path transfer function. This will be the single block. Now you can see here I have shifted this takeoff point to this point. You can see here. Now what to do? We have to add a block in series with is H2, which is having a reciprocal of this G5. See here. And since these two blocks are connected in series, I have simplified it and can be written as H2 upon G5. Okay. Now you can see here, this is again a feedback loop formed. You can again simplify it and convert it into a single block. Now you can see, okay, these they have first these two be connected in series, and then we can simplify it and convert it into the single block. Now these two again are connected in series. They can be simplified into a single block, and at last we can connect it into a this will be a feedback loop and can be converted into a single block. Now Ys upon Rs will be equals to this quantity. So this is the transfer function and can be represented into a single block. Okay, that's all for today's lecture. Thank you so much.